Hey everyone, and welcome to This Explainer. I am absolutely thrilled to be with you today on behalf of Forge College. So, in our last lesson on overloading and overriding practices, which is part of our advanced function implementation module in the Solidity from Zero track, you did some genuinely incredible work. You really mastered the art of creating these highly capable shape-shifting functions. But let's just be honest for a second. If you look at your smart contract right now, it probably looks a little bit like a chaotic explosion of scattered functions, right? You've got all these powerful tools lying everywhere, but absolutely no workbench to organize them. Well, today we are going to fix exactly that by learning how to design modular function groups.
Okay, let's dive into this. We've got a pretty solid blueprint today. First, we're going to tame that code chaos, then split our contract into two utilities groups, account and math. After that, we'll run some diagnostics to verify our work, and wrap up by seeing how this beautifully structured setup teases up perfectly for gas optimization.
All right, part one, taming the code chaos and organizing our schematic.
Look, I want you to think of code organization not just as a stylistic choice, but as absolutely vital safety work. Which brings us to a big question. Why do we actually need to group functions? I mean, why can't we just leave our highly capable overridden functions lying around like loose gears on a workshop floor? Well, in Solidity, a scattered contract is a vulnerable contract. Without distinct groupings, it's basically impossible to track which function modifies state, which one just reads data, and which one is secretly a foundational gear that absolutely no user should ever touch.
And that brings us to this really crucial concept, the API surface. Think of your API surface as essentially the exposed control panel of external and public functions. It's the buttons outside callers can interact with. We absolutely must group our functions to purposefully minimize this surface. You want to keep the dangerous internal state-mutating gears safely locked behind a really simple, highly predictable control panel. Simply put, if an external user doesn't need to push a button, that button should definitely not be on the outside of the machine.
So moving on to part two, the two utilities groups. Let's divide up this blueprint. To show you exactly how this works in practice, let's look at a master schematic. Notice how clearly we're dividing responsibilities here. Over on one side, we have our account utilities. This group handles stuff like get balance and deposit to. It uses a mix of external and internal visibility, and its one and only job is reading and updating per address balances, so it's very state heavy. Then, on the other side, we have our math utilities. This group features functions like sum and mulclamp. These are strictly public and pure, and their job is just to provide deterministic calculations. It's entirely logic-heavy. By separating out state management from raw logic, we instantly make our contract so much easier to read and, honestly, immensely safer. Moving right along to part three, account utilities. Let's talk about managing that state. All right, grab your welding torch, because we're building our very first subassembly. Within our account utilities, we have to draw a really hard line between what the world sees and what the machine hides. External and public functions, those are your user-facing entry points. They're the shiny levers on the outside of the box. Internal and private functions, on the other hand, do all the heavy lifting. They're the greasy, spinning gears inside the chassis. It is an absolute, non-negotiable rule of Web3 engineering that these internal helpers should never, ever be directly exposed to the outside world. So let's look at the specific functions in our account utilities blueprint. We've got getBalance, which is a public view function. It just looks at the state. Then we have deposit to, which is external. This is the exact entry point a user is going to call to add funds. And finally, we have underscore increase balance internal, and this one is marked as internal. This is our hidden state mutator. And hey, notice our strict naming convention here? We use a leading underscore and an internal suffix. By doing this, any engineer looking at the code instantly knows this is a hidden gear. Basically, if you see an underscore, keep it inside the machine. Part 4. Math Utilities. Time for some pure logic. Let's shift gears to our second module. If the account utilities are the storage tanks, the math utilities act as the deterministic brain of our machine. And to build this brain correctly, we really need to master mutability, specifically understanding the difference between view and pure. A view function is kind of like checking a pressure gauge. You're reading the current state of the machine, but you aren't changing a thing. A pure function, however, does raw, deterministic math. It doesn't even look at the pressure gauge. It just takes inputs, crunches the numbers, and spits out an output without touching or even acknowledging the machine state whatsoever. So here are the pure math helpers for a module. We have sum, which is public pure and safely adds values together. And we have mulclamp, also public pure, which multiplies values but enforces a strict maximum cap. Honestly, the Solidity compiler absolutely loves pure functions. It treats them like VIPs. Why? Because a pure function guarantees beyond a shadow of a doubt that it won't accidentally trigger any rogue state mutations. It's just clean, predictable, beautiful math.
All right, part 5. Verify, compile, and check. Time to run the diagnostics.
Okay, so we've built our 2 modules, and now it's time to run diagnostics to make sure our visibility rules are actually holding up under pressure. The crucial point here is that we must follow a rigorous 4-step test. Step 1, compile the contract. It should compile cleanly with absolutely 0 warnings about visibility. Step 2, invoke your read-only functions, like getBalance, just to ensure they return 0 initially. Step 3, invoke your state-mutating entry point, like deposit2, and then check the balance again to verify the state actually updated. And finally, step 4, call your pure math helpers independently to ensure they return the correct results without needing any state setup. If all 4 steps pass, you know your internal helpers are completely hidden and your external controls work perfectly.
Now just a few quick debugging tips from the trenches. If your compile fails, double-check that your function calls actually match the declared visibility. Also, if you're testing in Remix and your balances just aren't updating, please ensure you are using transact for state changes. I cannot tell you how many brilliant developers I've seen staring at a screen in total frustration for hours, practically pulling their hair out, only to realize they were just running local simulations instead of actually transacting their state changes. Oh, and finally, avoid making tiny helper functions public if they don't need to be. Keep that API surface minimal. Okay, let's move to our final topic. Part 6, preparing for gas optimization. What are our next steps? So you might be wondering, why did we go through all the trouble of organizing this blueprint? Why separate the math from the state? Well, it all comes down to this golden rule. Expose only the small API that external callers need. When you have a really minimal API surface, you drastically prevent accidental misuse by users or other contracts. But more importantly for you as an engineer, it makes future refactoring incredibly safe. If you ever need to upgrade the gears inside the machine, you can do it without changing the buttons on the outside.
And that brings us to the ultimate payoff. Because we've taken the time to create these beautifully isolated modular groups, we have set up the absolute perfect baseline to tackle gas optimization patterns in our next module. You'll be able to optimize the account utilities or fine-tune those math utilities entirely independently without worrying about breaking unrelated logic. Structure literally unlocks performance.
So I want to leave you with this final architectural thought. As you review your code today, ask yourself, are your internal gears safely hidden behind a minimal control panel? Keep those internals safe and keep your public API clean. Thank you so much for joining me for this explainer on behalf of Forge College. Make sure you visit forge.college to dive deeper and master even more Web3 engineering concepts. Keep building, keep organizing, and I will see you in the next one.